Hey viewers, welcome back to the channel, and today let's solve our system design problem. So today we will be designing a distributed message queue system. So let's have a look at the problem statement initially. So we have a backend system which is generating a lot of these events, and we have a notification service which is responsible for sending the notification for those events to the customers. So what would the possible flow look like? So if you talk about a synchronous flow, then backend will make a connection to the notification service, and then the notification service will send that back to the customers. This kind of approach has its own problems, right? So suppose backend generates them in a range. Suppose we have 100 to 200 notifications being generated per second, right? Those events, and then the notification service has a hard limit of just 50 per second. And then if we're doing it in a synchronous manner, then we have the downside of computing a lot of these resources on the backend, which is a big downside. So one of the possible way to do it asynchronously is by using a message queue. So a message queue would be temporarily storing these messages by providing an intermediary platform which allows the components to access the queue, and then the notification service would just be consuming those events which are put into the queue by the backend, right? So backend becomes our producer, and this notification service is the consumer in this case. So let's have a look at how this would look like. So we have the producer, which is producing all the different messages, and there can be multiple such producers. And then we have a consumer who is subscribing to a particular queue, and it's consuming those messages. And in this manner, we can have multiple such queues over here. Okay, so we can have Q1, we can have Q2 to Qn, and then similarly, we can have multiple producers and consumers who are just producing and consuming these messages is in an asynchronous fashion. So now this problem statement will have its own functional and non-functional requirements. So the first task would be to gather and scope out the requirements of the system, and given the limited time which you have for the interview, so it's around an hour or so in most of the cases, it's best to have a good discussion with the interviewer about what are the requirements and scope it out first, so that just to make sure that both of you are in the same page and there are no such ambiguity before you proceed to design the system. So in this case, let's talk about the functional and the non-functional requirement from our own side. So if we talk about the functional requirement, we would need to be able to send the message to the queue, right? So the producer would be responsible for sending the message to the queue, and then we have the receiver who would be responsible for consuming those messages or receiving those messages from the queue. And apart from that, we will also need an API to create the queue. So given the name of the queue, you can just create a queue with that, I mean, by using this API, and it can have more operations. For example, you want to support auto creation of the queue. Suppose you're sending a message to some queue which doesn't exist, then we would want to auto create a queue by that name, and all these configurations would be supported by our system. And then we have the delete queue API, but it's a bit controversial thing because it's a destructive action, so you can have some discussions with your interviewer about what are the requirements, if at all we need to do that, and if it does, then you will have to expose via command line utility, because it should be something which should be done by the admin, or yeah, it's a destructive action, so you need to be careful about that. So better to have a discussion about this before proceeding with actually implementation and designing the system for that. Now, talking about the non-functional requirements of the system, so being a distributed system, we want to achieve all of the good things about it. So we want a system to be scalable, so that yeah, we can just scale up and down as per the requirements. And apart from that, it should be durable also, so that yeah, it can tackle all the different faults and failures along with high availability, and at the same time it should be performant as well. So these are the main functional and non-functional requirements, and I would strongly suggest to have a thorough discussion with your interviewer, so that both of you are on the same page before actually proceeding with designing the system, so that yeah, it doesn't end up in a weird manner after or during the interview process. So let's have a look at the top level design of the system, and we'll just go over quickly the different components, and then we will individually go deeper into each one of them. So if we see that, how the flow would look like is we have a message coming in over here, and this will hit our global server load balancer, and then it will go ahead to the API gateway, which will fetch all the information from the metadata service and do some pre-processing on this particular message. And then provided things go well, then we were going to go ahead and put it on our backend clusters over here. And similarly, this message would be consumed by the consumer via this flow. So maybe the consumer will make an API call to retrieve all the messages via the offset, or maybe they have it being delivered via WebSockets. So yeah, those are some different ways of consumption of those messages, and it's better to have a discussion about whether you want an API for that, or maybe it's fine to have it over delivered by the message queue to the consumer, right? So now let's have a look at the different components. So the first component over here is our global server load balancer. So it consists of a DNS resolver, which will basically resolve it to the nearest data center which we have. So suppose our service is running globally in different regions. So we'll route the request to the nearest data center to have the lowest latency, and from there we can have multiple load balancers, because we want to be able to scale them as well, as we don't want a single point of failure. So there would be multiple data centers which our service would be running in, and then also the load balancer can also be scaled up and scaled down, because yeah, we don't want a single point of failure. And then we have the API gateway over here, which is responsible for things like authentication, authorization, and talking with the metadata service and our backend clusters, right? And also for things like caching and monitoring as well. So that's what the API gateway is responsible for. And then we have the metadata service. So as the name suggests, this is it's like a facade over here. So we have a service sitting connected to the metadata database. So this DB holds all the information about the queues which we have, when it was created, what are the possible admin actions which can be performed. So all that information resides in this particular DB. So we'll have a look at the internal workings of this when we come to this. And then the main component of our system are these backend clusters. So these are scalable nodes, geographically distributed, which holds the messages coming for the different queues, and it's a highly scalable system, and it has some special characteristics which we're going to see once we get deeper into our backend clusters. So let's have a look at the first component, which is the global server load balancer. So our GSLB is responsible for load balancer distribution, and it's as I said, it's a geographical load balancer which would route it to the nearest data center, and it also is responsible for health monitoring and for analytics, and as it can also scale up and down as per the needs. So suppose we have a request coming in like this in this fashion. So it's gonna first hit the resolver. So the resolver will yeah, just send it to the nearest data center which our service is running in, and this can be configured, right? So we have, this is a DNS resolver, and it's gonna resolve it to whichever the nearest data center which we have, or maybe the one which is the nearest is down, then it's going to take care of routing it to the one which is in the nearest proximity to that particular center. Suppose we have one running in US, in EU, and in Asia Pacific, then yeah, we can just route it basis on where the customer is currently located in. And then this is gonna go via the load balancers, which are themselves scalable as well. So you can add more and more nodes to our this load balancer, and this load balancer would also be like in a multi-leader configuration. So it's gonna take care of routing requests to some other nodes in case the node is facing some issues, some network partition related issues, or maybe the node just went down. So this is also an individually scalable component in itself. And after that, it moves on to the API gateway. Right, so this is our load balancer, and trust me, a load balancer in itself is a distributed component. So we're gonna tackle this in some another video when we're gonna deal with that. And moving on from the load balancer, the next step which we have is the API gateway service. So it's a stateless service, as we want to be able to scale it as and when necessary. So this is a stateless service, and it's a lightweight service, to be honest. And this is responsible for things like a validation of requests, authentication, and rate limiting is also one of the major features of the API gateway. Now, similarly, rate limiting itself is a big topic in itself, and you can have multiple algorithms being used for rate limiting. For example, the leaky bucket algorithm, and this is going to be out of the scope for this video, and we'll be tackling rate limiting in another video where we see how to design a distributed rate limiting system with different algorithms which are out there. So yeah, for now, just assume that it uses some standard rate limiting algorithm just to make sure that the requests are being throttled if a customer or a particular user is going beyond their subscription. Because think of it as a service where you have customers who have some SLAs, and you have some plans, for example, a maximum of 100K requests per minute, something like that. So if it goes beyond a certain number for some customer, then we want to be able to rate limit those requests using some standard rate limiting algorithms. Now, this is also responsible for usage data collection, because as I said, we want to be able to bill our customers. We also want to use the analytics and see how a service is being used, so that we can plan the maintenance activity accordingly. We can plan upgrades and updates, and maybe we'll want to be able to scale up or scale down our service as per the current usage statistics are going. And then the next thing is caching. So API gateway can also be used for caching. Suppose we want to be able to get some data about some queue from the metadata service. Then instead of making another and request to it, we want to be able to store it in some in-memory caching system. Maybe we can use Redis for that. So caching is also one such thing which we want to be able to use for the API gateway. But along with that, also keep in mind that we'll need some robust cache invalidation as well. So whenever some queue metadata is being updated, we want to be able to yeah, just flush out that cache from suppose we're using Redis, right? So we'll need that cache invalidation as well when if you're using it for caching purposes. Now, and the main function of this API gateway service is to act as an interface between our backend and the metadata services. So yeah, it's a lightweight services, and these are some standard operation, which it's not just limited to a distributed message queue. Rather, in most of the distributed systems, it's very common to have something like this API gateway. Right, now let's move forward and talk about a metadata service. So metadata, as just we discussed previously, is it's used to store the queue information. So what all things consist the queue information? It can be the name of the queue, when it was created, what are the limits of this particular queue, like what are the request numbers which we have to support for this queue, and maybe some other role-based access control things about that queue. All that information can be stored in our metadata service. And it would also support the creation and deletion of queues, right? So would have the API for that, as we discussed earlier. And yeah, organization based policy, validation, auto queue creation, all that can be stored as parameters, maybe as org flags in our metadata DB. And throttling policy and limits management, all of these things are being stored and persisted in the metadata DB, and we have the service which acts as an interface for the metadata DB. And cache invalidation is also something which, along with API gateway, can be handled at this metadata service, and it is something which is read intensive. So if you talk about the workload of this service, right? So if you compare the read versus write load, you're not gonna do so many write operations when you compare that with the read operation, because the read is gonna be very heavy, because for all the requests coming in, we want to be able to fetch the information of the queue where this will be going. So this is a major pointer about this particular service, and we want to be able to make the choice of the data storage, whatever we are using for the metadata service, based on this parameter. So this is read intensive, and the number of writes are kind of low when you compare them with the number of reads. Also, you might have one question: why do we actually need a metadata service? Why can't we just go ahead and make an API call, or just do a DB query from the API gateway service itself, right? So now there is a reason why we use this facade pattern. So suppose tomorrow we want to move to some other database providers. Suppose we're using some typical relational service at the moment, which works fine, but maybe we want to move to some document-based DB store. In that case, you'll have to make a lot of changes in the API gateway service itself. So you see that coupling coming in. So it's better to delegate that off to this metadata service, or think of it like a facade pattern. Your API gateway doesn't really know how which data store is being used, how it is being used, and then similarly you can even use this metadata service with some other service. So there should not be any coupling between API gateway and the metadata service. So for that, we are putting this facade service right in front of our metadata DBs, and that's the main intention of putting the service, so that we can have the decoupling. And yeah, in future, if you're planning for any major changes, you don't have to do any cascading changes just because the initial design wasn't so good. Now let's talk about what is the kind of data store which you want to use for this service. So if you talk about data store, right? So it's a big decision which needs to be taken, and you need to really justify this to your interviewer. Like, well, why is the reason why you're choosing a particular data store? Because it's never a best case scenario. Rather, given the kind of requirements you have to choose the best data store possible. So what are some of the main pointers which we have realized up until now, right? So we see that it has low writes and very heavy reads. Okay, so this is one factor which comes in about what data store to be used for such a service, right? So yeah, we have different data stores for such cases. If we talk about and relational data storage, then a well and fine-tuned DB like MySQL or Postgres is going to work fine, but there can be occasional spikes in the write. Suppose a particular customer is creating a lot of new queues, right? So we have that auto queue creation feature, right? So how do we handle the sudden spike in the writes? So that's one thing which we should think about. And then let's talk about the second factor. So we don't have many complex and multi-join queries, right? So one big advantage of the relational DB store is that the multi-join queries and complex query are very well suited for those DBs, because that's what they're built for. That's the relational part which they're actually optimized for quite a lot. And then we want to be able to partition it for scale. So suppose tomorrow we have a lot of users coming in and a lot of queues being created. So we want to be able to partition our database easily, and it's best to use some data store which can do it on its own. So it should be inherently supported by the data store being used. So that's another parameter which is going to affect our decision. And the next thing is that we want it to be able to replicate it, so that yeah, we have high availability. So that's another something which should be supported inherently by the currently data store which we were using for this. And then if you talk about the asset compliance, it's not something which we really require, right? So we don't want transactions, and we won't want strong asset compliance. So what do we realize after going over all these requirements? We clearly see that we don't really require the things which relational DBs are famous for, particularly this, like no complex multi-join queries and also strong asset compliance. But we see that the strong points of a NoSQL, or better to say them as document databases, for example, low writes and very heavy reads, and occasionally they can handle high spike in the write operations, and they support partitioning as well. Like you can partition it, or shard is some other word which is being used for that, and replication is also supported. for such data store. So we can clearly see that a NoSQL data store would be a better choice given the kind of requirements which we have for the system. And suppose so for example, Cassandra, one good thing about it is that it supports low writes and very heavy reads, but at the same time, it can very well support occasional spikes in the write operations, right? So Cassandra is definitely a good contender for the kind of data store which you want to use for this. And yeah, you can just have a good discussion with your interviewer on this point, and make sure to talk about the different requirements, right? So this will very well put you in a very strong position in front of your interviewer, that okay, you have the capability to discuss and put down the requirements and choose the best data store which is to be used for the kind of operations which you want to do. So I would strongly recommend to go over the different data stores available and how would you justify the one which where is being used. And trust me, we're going to make another video on the different column oriented NoSQL, SQL, document DBs. So we're going to go over all of that in another video. But yeah, this is how I would say you would structure your requirements and then choose a data store which is the best for the kind of requirements which you have. So let's talk about the metadata service data flow. So we have the request coming in. You can see this is the request, the blue one, and then you have this is the response going out. And this is a metadata service, right? And we have a routing tier over here, and we have different partitions of the data. So supposing that we're using Cassandra in this case. So what really happens is a request comes into the service would make a call to the routing tier, and suppose we want to fetch it for some random queue. Maybe suppose we want to fetch it for my queue, and we have partitions based on the name of the queue. So suppose we're using it just to keep it very simple. Suppose from A to E lies in the first partition, from F to M lies on the second one, and from N to Z lies on the third one. So we see that it starts with M. So we're going to go over to the second partition, which is this one, which is going to be N1, right? So the request would be routed to here, and from N1 we're going to fetch that data and we're going to just return it back in the response, right? So now talking about the partitioning, right? So there are different ways to partition your database. So you can just go, so a very naive approach would be just to go over by the name of the queue. I mean, you can just take the first letter and you can just use it for putting it accordingly, but that might not be the best approach because it's not really randomized in order. So suppose you have some queues starting with the letter G, right? So all and the so a particular customer is using all their queues starting with the letter G. So all of them would land on this node itself. And suppose there is a very heavy read and write operations having going on for that particular queue. So what would happen is node 0 and node 2 won't have that much of a load, but the node 1 is going to become an overheated node, right? Because it's going to take a lot of load in this case. So which is going to just which is just going to make the partitioning useless, because that's the main point of partitioning, so that you can evenly distribute the load on the different partitions of your DB. So one good approach or one good way to do away with this problem is to use some hashing functions. So suppose you can go for something like MD5, and what you're gonna simply do is put the name of the queue in that function and just use the hash of the name, so that yeah, that's going to be a better way to distribute the load across the different nodes, because now it's going to be pretty much randomized, right? So for different queue starting with the letter G. Now, when we are using some hashing algorithm, so the load is going to be routed to N0, N1, N2, and maybe all the different partitions which we have. So that way we're going to be able to distribute the load more evenly and prevent the problem of hot nodes and some nodes which is going to be idle nodes. Right, so this is one approach to do away with hot nodes, and yeah, it makes sense to just put down this as this point as well in front of your interviewer, right? Now we see one more component sitting over here, which is Zookeeper. So what does this do? We see that we have different partitions, and then we can also have multiple replications as well, right? So Zookeeper is basically an in-cluster manager, and all nodes are going to register them with Zookeeper. So suppose some node is going down, so we're going to have the replicas of that node, which is going to be uh, made the leader if that particular node goes down. So all that in cluster management and taking care of all the distributed nodes and the workers is going to be coordinated by Zookeeper. So Zookeeper is our coordination service, which is going to be managing all the different partitions and replications, and will take care of all the failure and faults happening, be it network partitions, be it failure on some node, or suppose with nodes going up and going down. So Zookeeper is going to handle all of that for us. So it's the in-cluster manager and basically the coordination service for our distributed workload, which is running for our metadata service. Right, so now let's move ahead and talk about backend cluster. So this is the main component of our system, the backend system, right? So it's something which we're gonna have to put a lot of thought about how to design this data store, because it has some very special requirements. So unlike most cases where we have a very read heavy and low write, or maybe a very high write and low read, so that's a kind of combination which you're going to see. But if you talk about our backend clusters, right, so we have very heavy read and we have very heavy write load as well. So we have a lot of messages being written to for the different queues, and at the same time we have a lot of consumers who are going to be reading those messages. So we're going to need to design a data store which can tackle very heavy read and very heavy write loads, right? Talking about the second one, so it should be highly scalable. That means we want to partition it into different sections, just how we did how we did for the metadata service. And then we also want to be able to replicate it just for the durability need which we had, right? So suppose one cluster, so one particular node in a cluster is going down, then we want one of its child to become the leader so that it can accept all those reads and writes. So all it should be able to handle all the faults and the failures happening. So now the question comes, where should we put all this data? Should we go for a database like some non-relational or some relational data store, or rather should we go for some disk storage? So I would strongly recommend you to take a pause and think about what do you think would be the better choice for our storage service. Okay, so let's go ahead and see why we should go for a disk storage, right? So yeah, disk storage is the one which we're gonna use, because if we talk about other providers like RabbitMQ and even Kafka, they store it on the disk. The only reason for this is you can just say that, okay, we're gonna use some store like HBase, or maybe Cassandra, or maybe CouchDB, Voldemort. But to be very honest, right, given the kind of load, it's best to go for some disk storage, so that you can just put them on the hot storage disk, and then you can easily just pull that data out. You can put that in, and it's very easy to scale it. You can just add more disk to be able to scale it up and down, because if you go for some traditional data store like some column or some document base or some relational store for this, then it's not well suited, because we have very heavy reads, but at the same time we have very heavy light write loads as well. So we want some store which can we want to avoid the overhead of the internals of the database, right? So we have those B trees and other structures. We don't really need that, because that's going to impede the throughput of the system. So this storage would be the best way to go ahead and yeah, using the system, right? So let's see of how this is going to work. So you can easily relate it with the API gateway we just saw. So if you talk about the different components, so we have a routing tier manager, right? So this is gonna take in the name of the queue and the current offset, any which we want to read about, right? So here also we would be using the hashing algorithm. So suppose we have a queue by the name of, so we're gonna generate the hash of, suppose we have a queue by the name q1, then it's gonna give us some random hash value like MD6674, right? So this is gonna be the hash value of this particular queue name, and this routing tier manager would, after generating this, would then just have a look at which partition would that be stored in. So, and partition, just like that, we can decide on how we want to partition this. Like this hash value can be the key on which we can partition it into different A0 to N partitions, right? So we have this partition running in over here, and for each partition, if we want to go ahead and see how that looks like, so we have a leader for each partition, and this leader accepts all the read and write requests, and at the same time we have multiple replicas, right? And before I say anything else, so we can always scale up and scale down the partitions. Okay, so if we want, we want to scale it to more partitions, we can add a few more of them, and then we will need to move data across partitions, which yeah, it's something which is an expensive operation. So initially we want to be able to create a good number of partitions. So suppose you should already have around a few hundred or maybe 1,000 partitions already created, right? So that's one of a good approach, so that yeah, you later on don't have to move data across partitions as you scale up or scale down. So that's something which you can have a discussion with your interviewer, so you can suggest some approaches for that, and yeah, then accordingly you can just put forward your reasons for that as well. Now once we have done a number of partitions, so inside of partitions we have a leader which is responsible for all the load, as I just said, and then this leader will also have multiple nodes as the slave nodes, right? So it would replicate all that information to these slave or these replica nodes. So what happens is, in case of a failure, suppose leader 1 goes down, so what's going to happen in that case? So suppose leader 1 goes down, so in that case, we have the zookeeper running in over here. So one of the replicas, suppose replica 2 is gonna get promoted as the leader of this particular partition. So this becomes the leader, and all the requests from now on would be would be sent to this particular leader which we have over here. Right, so this becomes the leader for this, and it's gonna now be responsible for replicating it to the different child nodes, right? And whenever a leader one, like the main leader comes back, we'll need some algorithm to handle with those cases, because there can be conflicts. The leader might think that it's still the leader, so there are ways to shoot that node, and maybe we want to be able to put that back, or maybe we want to be able to replicate the data on that particular node we just came back. So for simplicity, you can say that a zookeeper would be taking care of those all the different use cases, and it's best to not dig too deeper into these things, because yeah, you would be bounded by the kind of time you have. So just discuss of all the different horizontals and just go very deep into some of the aspects if your interview wants you to go down into them and have a more thorough discussion on those points. So this is basically how our this backend server would work. So we have a lot of disk storage which are storing those messages, and then we also have offset, right? So we every request can tell you the offset till where I have read, so that yeah, you're well going over all the messages for that particular queue, you can just go till that offset and just provide the consumer with all the messages after that particular offset. So all these things, the low level items would also be managed via some storage manager which is running, or some host level services which are being run on these hosts which are storing the message for our system. Right, now let's talk about some key discussion pointers of our system, right? So this is a complex system in itself, and there are multiple things which if you want, you can go ahead and discuss with the interviewer, and maybe your interviewer might ask you to dig a little bit deeper into those points. But still, from your side, it's best to just talk about or just enumerate these points, so that yeah, the interviewer knows that okay, you do have an understanding of the systems, and yeah, these are kind of application to multiple such distributed system. So one is a security aspect, right? So we want to ensure that all the requests coming to the system and flowing out are encrypted. So you can use SSL and TLS for that. And internally also, when you're storing the messages on the different nodes, right, then we want to store them in an encrypted format. So security is an essential part of our system. And then monitoring and alerting, right? So you want to go ahead and use something like OpsGenie, because suppose some node is going down and or coming up, or maybe there's a partial data center failure or something like that happening, then we want to be able to aware of all those things. So it's best to talk about these aspects, for example, security, monitoring, and we want to have alerting system as well, so that yeah, we can know that okay, something like that is happening. Now we're gonna just discuss two important things like queue delivery order and business event order. So suppose we have this queue and we have two events coming in A, and we have coming in B, right? And suppose A comes first and B comes second. So if we talk about what is going to come out first, who's going to come out first, A or B? So we would say that okay, A should come first and B should come second. But this kind of queue delivery order, to be very honest, is not something which is really required in the first place. Because if you want to go ahead and uh, implement something like that, it's gonna be very inefficient to guarantee this kind of delivery order, because then you want to serialize things, and then you won't be able to take care of uh, the asynchronous pattern and the other things, because there are some downsides, or there are kind of some issues with distributed systems. But to be very honest, trust me, this kind of delivery order is useless. We won't really want to guarantee that which is going to come first, and even some solutions out there don't really guarantee this kind of a business queue delivery order, right? And it's not something which is desirable as well in the first place, right? So now let's talk about business event order. So suppose, to give an example, suppose we have two events, right? So suppose we have the balance going from 0 to $1,000, and then we have another event which where it goes from 1,000 to $500. Okay, maybe this person just made a purchase. So what happens in this case? Okay, suppose we are emitting both of these events at the same time. So when the consumer is consuming them, right, so we have a casual order or casual relationship before in them, right? So the balance first has to go from 0 to 1,000 before it coming down to 1,000 to 500. So if we want to really implement something like this, then then again, that's an inefficient thing, and it's not something which should be implemented at the broker level. Rather, for this we can have a consumer level ordering for this. So what basically happens in this case, if the downstream receives the event that 1,000 to 500, this is the first to be received, then the 0 to 1,000, okay, this is the second event which is coming, right? Suppose this is the first, this is the second, then it must be able to identify the two messages that are out of order. Maybe you can use something like timestamp. Maybe you can use something like a message. A producer can add some sort of some number, okay, that I'm producing messages in this sequence. So it can add a sequence number, it can add a timestamp value from its end, and that can be used at the consumer, whoever is consuming the messages, to be able to identify whether they're out of order or not. And we don't want to do it at the broker level, because there's a lot of downsides to it, because even system clocks can get unreliable at times. So yeah, we would in this case assume that queue delivery order and business event order, these cases are being handled at the producer and at the consumer level itself, right? So we don't want our system, we would really don't want to overload our system with all these different things, because it's going to bring down the throughput of our system. And the next thing is the delivery semantics. So we have at most once, we have at least once, and we have exactly once a kind of semantics. And most system, they kind of guarantee and at least one semantic, because it's really hard to guarantee at most ones or even exactly ones, because that's also going to bring down the the throughput of our system. So these are some key pointers which you should also put forward and discuss with your interviewer, right? So yes guys, that's it about the system. And yeah, in case you have any questions, feel free to put them down in the comments, and I'll see you guys again with another video on system design pretty soon. Stay healthy and goodbye.